All right, and our fifth learning outcome or skill, more appropriately, I can write an explicit equation. Sometimes we call this an explicit rule. It's generally an equation. I can do that for arithmetic and I should really say and because I want to do it for both, arithmetic and geometric sequences. I wrote geometric function. I mean, it's not really that wrong, but we've been referring to these as sequences using function notation. So we remember function notation. Remember, an explicit equation is one where there is an input and an output. And when you are learning about linear equations, oops, sometimes my pen just doesn't want to cooperate. When you learn in 8th grade or even in 7th grade, when you learn about like proportional relationships, you either learn something like y equals k times x, where you might call k the constant of proportionality. Or so like, for example, y equals 5x. Or more appropriately, like in 8th grade math, when you're learning about equations in the form of y equals mx plus b or b plus mx. We call that slope-intercept form. If I see something like y equals 2x plus 4, if I plug in like a 7, for example, for x, that would be my input. And what I get from that y value that it gives me, oh man, I don't know, my pen's being so finicky. But the y value that gives us is our output. So just pretend it says output right there by the y. It's not letting me write on it. I'm not sure why that's happening. Okay, so in function notation, we said we're often using n and f of n. In math, we love to use x and f of x, but that'll come a little bit later for us. So in 5a, I'm going to try to write the explicit equation for the function represented by the table below. And there are infinite correct equations, but commonly, like there's, I think, 2 things that we're going to come up with here. So in 5a, what I'm first going to think about is what's the pattern I'm seeing? Is this sequence arithmetic or is it geometric? And I usually check to see if it's arithmetic first. So since I already know that 5 plus 7 is 12, or again, working backwards, I could just do 12. Whoops, you know what? I'm actually going to write this in kind of up here. I could do 12 minus 5 is 7. That tells me that I could add 7 to 5 to get 12. Let's see if that pattern holds. 12 plus 7 is 19. 19 plus 7 is 26. Good, I didn't make a typo because it is supposed to hold. Nice. So we see that common difference is 7. So that means that this is an arithmetic sequence. And we've talked about how arithmetic sequences, when we plot the points for our sequence, that they appear in a line, linear. And we said that things that are linear might have an equation that looks like y equals mx plus b in function notation. So there's a few strategies that we've talked about in class, and we're going to really tighten this up, I think, in Unit 2. All right, I sure hope we're going to feel that we're tightening it up in Unit 2. Here's something that we've explored a lot in our class, is that if the first term in my sequence is 5, I can express each term as that first term plus the number of 7s it takes me to get to that number. So I know from that first term to my second term, I'm adding a 7. So when I get to my third term, 5 plus 7, well, that's 12. That's our previous term when n was 2. But I now have to add an additional 7. Or I could just think from 5, I have to add 7 twice to get to 19. Lastly, to get to 26, I've got to add 3 7s. All right, and I know that I added 0 7s to my original 5. Now, what I'm noticing is that I see something that could be generalized. That's a big part of how we think about mathematics, is can we make a generalization? So when I see repeated addition, Or repeated as subtraction, I could think of as adding a repeating negative. When I see repeated addition or subtraction, the operation that generalizes that is multiplication. So I want to express this now. I'm going to write this just underneath as 5 plus 7 times the number of sevens. And for some reason, I like to go backwards. I like to start with the most number of sevens. So for my fourth term, I was adding 3 sevens to that, to the 5, to my first value. All right, if I go back a term, I'm adding 2 sevens. If I look at my second term, I'm adding 1 7. Oh my gosh, and I see a pattern. And looking for patterns is a huge part of what we do in algebra as well. You shall learn. If you haven't figured that out yet, you shall. So what I'm noticing is that what I'm writing each time looks exactly the same, except for this number. That's the only thing that's changing. And I think if my pattern's correct, I should be able to write that. Does that work? So 5 plus 7 times 0 is 5 plus 0, which is 5. It does work. All right. When we get to that form, when we can write when I could write my sorry, I'm so tired. My brain's just deleting words from my vocabulary. When I can express what is happening to my function f, or f of n, when I could get to this spot where I see this one thing changing, remember, another word for change is vary. So sometimes in math we use the word change, sometimes we use the word vary, and the word vary reminds me of the word variable. And guess what? That thing that's changing is where our variable goes. But the question is it n? Is it n? Do I put an n there? Well, let's look. If I were to put the number 1 here, that wouldn't work out because I don't get a 1. So I can't just put n in parentheses. Let's see what happens. Nope, the 2 won't work, the 3 won't work, the 4 won't work. But how are those numbers related? How is 1 related to 0? In the same way that 2 is related to 1. In the same way that 3 is related to 2. In the same way that 4 is related to 3, and so on. Well, I noticed that the number in here is 1 less than my n value. So I could think of this as 5 plus 7 times n minus 1. And that will work. So that is one way that we can express this explicit equation. I could say f of n, and remember, I could almost think of this as x and y. That's just not function notation when I do that. Well, I could use function notation, I suppose. I could write this as 5 plus 7 times n minus 1. And alternately, remember that addition is commutative. So I could start with the 7 times n minus 1 and add 5 later. Those would be equivalent expressions for f of n. Now, we talked about this a little bit in class 2, but there's another way we could do this. And I'm going to point out something here that I don't know if you watched the video for item 4, but something I pointed out when we were looking at this table in number 4 is that 18, that number there was the first number of our function, and we saw n minus 1 in our pattern. But what if we could write that with just n, so not an n minus 1? Well, we have done this strategy in class a little bit too, kind of going back to that idea of our starting value. That would be when n equals 0. Even though for a sequence, it doesn't make sense to have a 0th term. We could kind of think it's kind of a thought experiment. What if I had a term 0? So I know that I'm adding 7. So what if I do 5 minus 7 and I get a negative 2? That works out, right? Negative 2 plus 7 gets to 5. All right, so that's if n was 0 and this pattern holds, f of n, or f of 0, would be negative 2. So what if I start at negative 2 as I'm thinking about those 5s and 7s? And so instead of a 5, I'm starting with a negative 2. I know I'm writing a lot of stuff under here, so I'm sorry. I'm going to do this in blue so that it's, I don't know, not a color I just use. Ooh, actually, let's do purple. Dark purple. Indigo. All right. I have no idea what the difference between indigo and blue is, but maybe one of you can explain that to me. All right, I'm going to start with -2. And from -2 to get to 5, I add 7. So I could express 5 as -2 plus 7. I could express 12 as -2 plus 7 plus 7. I could express 19 as -2 plus 7 plus 7 plus 7. This is just like what we did in green above with the 5, but what I notice now, what's different, is that the number of 7s I'm adding when I start when n equals 0, that number of 7s is the same number as n. And does that work every single time? I don't know. We might have to think about that more. But is that something I've noticed a lot with these patterns? It is. Does it remind me of slope-intercept form? Absolutely it does. So if I start at -2 and I add 7, now my 7, or now the number of 7s I add is the same as the number of what term I'm considering for my sequence. And lastly, if you are wondering to yourself, are these 3 expressions or equations, but expressions for f of n, are they really the same? Yes, they are. And you know how you can prove that to yourself? Is distribute that 7. I'm just going to pop this expression over here. I'm going to ditch the f of n equals for just a moment. All right, what if I distribute the 7? So I could distribute multiplication over addition or subtraction. I would get 7n minus 7. So don't forget, when we distribute, we multiply all of the terms in parentheses by that 7. And when I combine my like terms, I could combine a 5 and a -7, but I can't combine them with 7n. And this is something we'll practice a lot this year. But 5 plus -7, or 5 minus 7, is in fact -2. So look at that. What I love about this, and what I love about mathematics in general, is we often have so many different ways to check our reasoning. And so if you came up with either of these equations and you're wondering if they're correct or they're both correct, well, you could distribute and see if you get an equivalent expression on that right-hand side. And chances are, if you do, they're probably both correct. I mean, otherwise, I suppose you made the same mistake twice. But sometimes it's better to make the same mistake twice than to make a lot of different mistakes. But all right, let's look at, oh man, we got a few more examples. Let's look at this next table. Kind of same thinking as before. I want to start first. Do I have a common difference or a common ratio? Is this arithmetic or geometric? And I could tell it's not arithmetic because there's no way the same number I add to -2 to get to -8 is what I would add to -32 to make -128. So let's make sure it's geometric. Oh man, we got some big numbers. I'm going to find the common ratio by division. So -128 divided by -32. Woof. I certainly can do that math, but I am not above using a calculator either. I just wish my fake calculator would turn itself on. It likes to say it turned off. All right, if you're using the graphing calculator, down at the bottom where the enter sign is, oops, I just hit the enter button, to the left of that, there's it looks like a subtraction in parentheses. That's the negative symbol. The calculator is actually pretty picky about, it won't acknowledge the subtraction operator as a negative symbol, which is kind of silly. All right, -128 divided by -32 is +4. We knew two negative numbers divided would have a positive quotient. So -32, well, I could have just started with these smaller numbers. That is also a +4. -8 divided by -2, that quotient is +4. So that is our common ratio. We're multiplying by +4. And since our starting value is negative, everything's just getting more negative. All right. So now, just like we did before, I'm going to look at these two strategies real fast. So if I start with -2, I could think of -8 as -2 times 4 I could think of negative 32 as negative 2 times 4 again. Because again, I'm multiplying by 4. That's my common ratio. To get to negative 28, start with negative 2, multiply by 4, 3 times. Just like we saw above, I see something being repeated, but it's not addition. Now it's multiplication. So how do I generalize repeated multiplication? Well, we do that with an exponent. So I'm going to write this as, again, I like to start with the most 4s. I don't know why, that's just how my brain works. I'm going to generalize this as negative 2 times 4 to the power of 3. I'm going to go backwards one, negative 2 times 4 to the power of 2. I'm going to go backwards one, negative 2 times 4 to the power of 1. Oh, I recognize a pattern. I love it when I recognize a pattern in math. I'm going to go back one more step, because if this is correct, if my pattern's correct, this should be negative 2 times 4 to the power of 0. And any non-zero number to the power of 0 is 1, so that is correct. All right, so again, like we said before, what changes? What varies? Well, the thing that varies, I'm getting this expression that looks really similar, but the thing that varies each time is just my exponent. And I know that because it varies, that's probably what I'm going to place a variable or a variable expression. So when I look, the variable that I'm trying to get in there is n. And when I look at my values of n, similar to above, I started with my first term. They're not the same. Like where n is 1, that number's not a 1. It's 1 less than 1. It's 0. When n is 2, my exponent's 1 less than 2. When n is 3, my exponent's 1 less than 3. When n is 4, my exponent's 1 less than 4. So what happens when n is just n? Y'all, that's the explicit equation. What happens when n is n? Well, the same thing, except my exponent is just 1 less than n. Y'all, that's our explicit form right there. And yes, I did say y'all because I am from Georgia and I say y'all sometimes. Y'all means all. All right. So f of n is negative 2 times 4 to the power of n minus 1. That works for us. That's a good explicit equation. It holds. You could plug those values back in to check it. You could use that to generate other terms. But just like above, there's one more way to think about this. Well, that's actually not true. There's infinitely many more ways to think about this. But as far as common things that have come up during our class time together, ooh, I'm going to use the rainbow pen. Oh, that's thick. All right, I lied. I'm going to go back to a different color. All right, what if I considered what f would be when n is 0? That's kind of the other main way we've thought about it. And in the context of a sequence, that might not make sense. We don't usually have a 0 term. We start with a first term. But if n is 0, I could still think, what should f of n be so that this pattern holds? So remember, we said going through our sequence, we're multiplying by 4. So to go back a term, I could divide by 4 or multiply by 1/4. Those would be the same thing. So negative 2 divided by 4 is just negative 1/2, or if you like to call that negative 0.5, those are the same thing. One's a fraction, one's a decimal. So if I start with my 0 term, I'm going to notice that same pattern that I saw up above with the arithmetic sequence. That if I think of negative 2, if I start at negative 1/2, and I think how many times I multiply by 4, well, now I had to multiply by 4 one time to get to negative 2. If I start with my 0 term, when n is 0, negative 1/2, I have to multiply by 4 twice, so 4 squared. So again, you're like, why would I want to do it this way? Well, you might not. You don't have to. They're both correct, but this might help us with some thinking in our next unit, that when I'm starting when n is 0, and I'm using this starting value, I'm noticing that my exponent now does correspond with where I have or what my n value is. or rather what term I'm thinking about. So that just gives us one more way of writing this explicit. Sorry, I'm like writing in the margins. I probably should have made this bigger, but it's already a lot of paper. It gives us one more way to think about this, that I could start with the value of -1/2. And if I do that, this is now 4 to the n. And I don't think we know enough about our exponent rules yet to understand why these are the same. Like above, we were able to distribute that 7 combined like terms and see that these are the same. But I will tell you that we're going to learn some rules about exponents, and these expressions are in fact the same. I just don't think that you necessarily understand that yet, and that's okay. All right, in 5C and D, we're doing the same thing. The only thing that's different is we have a graph. And I don't necessarily want to encourage you to do this like one way over a different way. We're going to spend some time talking about how to write the equation from the graph. In 5C, I could see that this is arithmetic. I could see those points are in a line. We call them collinear. That's a good geometry term for you. And what I notice is that as I go from one point to the next in my sequence, I'm moving down to, I could call this the y-axis, or I could call this the f-axis if I'm using f of n. So again, I could either think of this as the x-axis, or I could think of it as n. So as n increases by 1, or x increases by 1, I'm going down by 2. And in Math 8, you probably thought about that as slope, rise over run. And you're not wrong about that. That's definitely going to come up. If we draw a line through those points, that's our slope. That's coming up in our next unit. So, well, it came up in this unit, but it's coming up again in our next unit. So if it were me, I might, right now, feel more comfortable writing a table of values. And you could use function notation. You could use x and y. I just want you to be comfortable with both, actually. So I could make a table of values. I started, and I'm not sure how well this printed for you. I've been having trouble getting my graphs to print. But when x is 1 or when n is 1, it looks like my y value is, let's see, 10, 11, 12, 13. When x is 2, well, we said we're going down by 2 and that we could see that in the graph. So when x is 2, y is 11. When x is 3, y is 9, and so on. And like you could keep going, but we probably have enough values to get our equation. So now I know that there's not a point on the y-axis, but kind of like we did in the table, or in the tables above, like we could make that point. It might be hypothetical. We don't usually have a 0 term in a sequence. But what if I went up 2 and back 1 to get to this point? Or what if I just know that 15 is the number that would come before 13 if my pattern is decreasing by 2? This is still powerful knowledge because that's our y-intercept. So if you're feeling really good, like if you remember from, I almost said Algebra 1. This is Algebra 1, isn't it? If you remember y equals mx plus b from middle school, from pre-algebra or algebra, whatever, Math 8, whatever you called it, we know that that m, our slope, that's the same as our constant rate of change. That's the same as our constant or common difference. So when I see that I'm decreasing, my y values or f of n values are decreasing by 2 every time x or n increases by 1, that's my slope. And this b is my y-intercept. So I could think of this as y equals negative 2x plus 15, because my y-intercept is the ordered pair 0, 15, but b is the y value, the place where that line crosses the y-axis. All right, now alternately, the way we've been also thinking about this a lot is if I start with that 13, if that's my starting value, then 11 is 13 minus 2 one time. 9 is 13 minus 2 two times. The next value in my table is going to be 13 minus 2 three times. So we're kind of thinking, it's like we're thinking recursively to get to my explicit, to get to where I can generalize. All right, so if I think about it this way, and I never found Like again, I'm assuming we didn't put that 0, 15 in our table if we're thinking about it this way. And again, I guess 13 is just 13 minus 2 0 times. I could also express my function f of n as 13 minus 2. Oh, I know I need a variable because it's the junk that I'm multiplying 2 by that varies. And again, I notice that the thing I'm varying by is not my x or my n value. In fact, it is 1 less. So that number in parentheses, is 1 less than what n is. So that's why I'm going to put 1 less than n, aka n minus 1. So generally, that's how we could get to our explicit. I know these look very different, but they're the same. They really are the same. Different notation, different ways of thinking about it, same. All right, last one. Oh my goodness, I'm so ready to be done with this. Number 5. Write the explicit equation. We've got a function represented in the graph, and y'all, I can see with my eyes that that is not a line. So I'm not saying that all curves represent geometric sequences. That is false. That is not a true statement. However, in this unit, where we're really just exploring arithmetic and geometric, this curve is probably going to indicate that we have a geometric sequence. But let's double check. We can make a table. When x is 1, I'm not 100% sure what y is. It looks like 1/2, but I don't want to guess, so I'm going to come back to that. When x is 2, y is 1. When x is 3, y is 2. So I'm just kind of labeling my axes here to help. You're always welcome to do that if they don't come labeled. And I'm going to make a table. And again, you don't have to. I think it's really helpful. I'm going to leave a space for my 0, but I've got values of 1, 2, 3, 4, and 5 for x. I said I'm not real sure about what x or what y is when x is 1, but I know when x is 2, y is 1. Then when x is 3, so like this point right here, y is 2. Then when x is 4, y is 4. Oh, I see what's happening. So this must be an 8, right? Let's check. 5, 6, 7, 8. Good, because you know what? If that wasn't an 8, I put that dot in the wrong spot. Beautiful. So now I could think backwards, and I could know for a fact that if I'm going down my table multiplying by 2, right? 1 times 2 is 2. 2 times 2 is 4. I know I could work backwards and divide by 2 or multiply by a half to get 1/2. And if I want, I could find what y is when x is 0. And y'all, I bet you want it to be 0, but it's not. It's going to be 1/4. So 1/2 divided by 2, or 1/2 times 1/2 is going to be a 1/4. We'll talk about this function later, but it's never actually going to be 0. All right, if I look at this sequence, again, if I start with my 1/2, I could think of this number as being 1/2 times 2. I could think of this number as 1/2 times 2 times 2. That would make this 1/2 times 2 times 2 times 2. And again, if we could take that one step further and generalize that with an exponent. So 1/2 times 2 to the first power. 1/2 times 2 to the second power. 1/2 times 2 to the third power. So that must mean this is 1/2 times 2 to the fourth power. Maybe check me in the calculator on that. That should also mean that this is 1/2 times 2 to the power of 0, which it is, because 2 to the power of 0 is 1, not 0. I get that might be weird. All right, so I got to this place where structurally I see a bunch of expressions, the ones in green, that look the same. And there's only one thing that varies, one thing that changes. We said a word for change is the word vary, V-A-R-Y, not very, V-E-R-Y. Those are not the same. I can see how that's very confusing though. Haha, pun intended. Okay, so if I'm looking at this, I'm noticing that the thing that varies is not the same as x. And if you're like starting to connect why that's happening, it's because we started when x is 1, not when x is 0. But you guys, that's okay, because what this number is my value for x minus 1. So 5 minus 1 is 4. 4 minus 1 is 3. 3 minus 1 is 2. 2 minus 1 is 1. So whatever x is, if I subtract 1, that gives me that exponent. So that helps me write this equation. So I could say I'm using the structure. Y equals 1/2 times 2 to the power of x minus 1. And in function notation, where this is n and f of n, that's going to be f of n equals 1/2 times 2 times n minus 1. Now, going back to what if we started here? Oh, I bet it's coming together. I hope it's coming together. I know this has been a hard unit. If I look at that very first, not even the first term, if I go back and find what y should be if x is 0, I get 1/4. Now I could think of all of these expressions as 1/4. This would be times 2 to the first. 1/4 times 2 to the power of 0. This is 1/4 times 2 to the power of 2. If I start at 0, when x is 0, the thing that varies, it seems to match my x value or my n value. So I could also express this y equals 1/4 times 2 to the power of x, or in function notation, 1/4 times 2 to the power of n. And again, we'll learn some more exponent rules this year, but these are all the same. They might not look the same, but they're all equivalent.